Next, let us talk about the serviceability requirement. There are quite a number of serviceability requirements that you need to consider when you design for reinforced concrete member. Some of those requirements are applicable to all the members, such as beam, slab, and staircase. Some of those are not applicable to certain members, depending on the situations. Without further ado, let us get started. First, we talk about the concrete cover. The concrete cover is normally associated with the durability of the structural element. You have reinforcement embedded inside the concrete, and there is a requirement of the nominal concrete cover, which serve as the protective layers to the steel reinforcement, protecting the steel reinforcement from corrosions due to the moisture, carbonations, chloride attack, sulfur attack, and other environmental deteriorations agents. A reinforced concrete can last long, at least 50 years, if it is properly designed and the serviceability requirements are fulfilled, especially this nominal concrete cover. These are the equations used for the concrete cover, which is applicable to all the members, beam, slab, and staircase. In fact, when you design those members, the concrete cover will be the first one to be determined, depending on the exposure class of that particular concrete member. The nominal concrete cover may vary slightly. Determining the concrete cover is very important, as later it's going to govern the effective depth, which you use to calculate for the moment resistance of the member, shear resistance of the member, and etc. The nominal cover is determined by the minimum cover plus the deviations that caters for the quality of the workmanship. Under normal circumstances, we will take these deviations equals to 10 mm as a precautions for poor workmanship and inaccurate preparations of the members. The C minimum is determined by three aspects. The first one is due to the bar size. Second is due to the environmental exposure. And the third, it should be at least greater than 10 mm. For more information regarding how to design for the concrete cover, you may refer to the previous videos. Next, we talk about the axis distance. The axis distance refers to the distance from the edge of the member to the center of the main reinforcement. It is associated to the fire resistance, where this axis distance shall determine the thickness of the protective layer of the concrete from high temperature due to the fire hazard. The thicker the axis distance, the longer the structural member would last in case of the fire hazard. These are the formulas related to the axis distance. For more details related to the calculations of the fire resistance, you may refer to our previous videos in the chapter 6 of RC Design 1. Bear in mind that the axis distance is not the same as the concrete cover. In terms of the purpose, designing the concrete cover is to determine the required thickness of the protective layer to the steel reinforcement both the shearing and the main reinforcement from being exposed to the environment, which can deteriorate the quality of those reinforcements. As for the axis distance, it determines the protective layers of concrete against fire resistance, reducing the rate of transfer of the heat to the main reinforcement that can jeopardize the strength of the reinforcement. The design of the concrete cover is determined by the exposure class of that particular element, whereas the design of the axis distance is determined based on the fire rating, how long you would like the structural element to last in case of the fire hazard. There is quite a series of the exposure class that you can use for the design of the concrete cover. There is also a series of the fire rating that you may use to design for axis distance. Theoretically, you have to consider both for you to conclude the final thickness that you're going to use enveloping the reinforcement. In the case that the concrete cover give you thicker protective layer than the axis distance, then the concrete cover will govern. Otherwise, the axis distance shall govern. Therefore, in the actual calculation, you will need to calculate both concrete cover. As their dimensions and their reference point vary slightly, you will need to do some simple conversion, converting the axis distance to the equivalent thickness of the cover. This can be done using the axis distance that you have concluded, minus half of the bar size and minus the size of the shelling, and then use the equivalent protective layers thickness compared to the C nominal for the concrete cover. Use the larger value that should ultimately serve as the design concrete cover for your structural element. Next, we talk about the L per D ratio. In the example questions for the revision, we have demonstrated the calculations for the L per D ratio for the beam and the staircase. In fact, the calculations for the L per D ratio is also applicable to the slab. The purpose of this L per D ratio is to prevent cracking due to excessive deformations of the structural element, particularly due to the bending deformations. These are the equations for you to calculate the L per D ratio, which serve as the limits, where the actual provided L per D ratio shall not exceed those limits. There are two equations for you to determine the L per D ratio limits. This is dependence on the relationship between the row and the row node. The row represents the percentage of the reinforcement bar required over the effective cross-sectional area, where the effective cross-sectional area is defined by the BD on basis of the effective depth of the beam instead of the actual height of the beam. Same principles goes to the slab and the staircase. As for the row node, it is due to the concrete strength FCK. By comparing these two parameters, if the row is equals to or less than the row node, you will use this equation. Now, if the row is greater than the row node, you're going to use this equation. As for the K, you can find it in the table 7.4 end of Eurocode 2. And the raw prime here represent the required compression steel bar areas over the effective area of that particular structural element. You can see in the summary table here all the structural element, beam, slab and the staircase would require the checking for the L per D ratio. Even though they are all required, their applications vary slightly. You are checking the deflections along the longitudinal spans of the beam, this one without any argument. But when come to the slab, you are actually checking against the shorter span. This is because a slab is more likely to bend in the shorter span as compared to the longer span. The shorter span, it will be the critical directions for the bending. Because of that, you're going to check your L per D ratio against the shorter span in the slab. As for the staircase, although in many aspects the design of the staircase is similar to a slab, due to its nature similar to the slab as a relatively large member. However, because of the support conditions of the staircase varied slightly from the slab. If you see the RC slab, a typical RC slab is supported by beams at all edges. That means all four sides of the slab is supported. However, when come to the staircase, the distributions of the load, it will be one way. A staircase is supported by two beams only. There are no beams on the other side of the staircase. Because of that, the bending of the staircase, it will be at the longitudinal directions. This links to the design for the L per D ratio for the staircase similar to the beam. Both are doing in the longitudinal directions. If you find this difficult to remember, you can always sketch the member and imagine the deformations of the member when it is subjected to the loads. The bending directions of that particular member will determine the effective length that you use to compute the L per D ratio. Therefore, for a beam, the L, it will be the effective length between two support, whereas for the slab, the effective length, it will be due to the shorter span of the slab. And for the staircase, the effective length, it will be the distance between two beam support.